So for question number 3, we're going to be drawing I3 minus. So let's look at the electronegativity values first. So we have 3 I's. So on the periodic table, I is in the same column as fluorine, which is the most electronegative atom with electronegativity of 4. However, as you move down the column, the electronegativity values actually decrease. So iodine actually is going to have an electronegativity that's actually smaller than 3. It's around 2.7. So are the bonds between the iodines going to be covalent or ionic? Well, since they're the same atoms, the electronegativity value difference is going to be 0, right? And this is definitely less than 1.5. So they're going to be covalent bonds. So how many valence electrons will there be? So each of the iodines have 7 valence electrons. So that's 3 times 7. That's going to be 21. However, don't forget that it's I3 minus. So the minus, with the minus, we have to account for that plus 1. Plus 1 more valence electron, right? So we get a number of 22 valence electrons. Always make sure to account for the minus, or if it's a plus. If that's an easy mistake to make. So is this structure going to be hypo, hyper, or an octet structure? So we know that the iodines, like the halogens, they participate in single bonds usually, right? They're on the ends of the molecule. However, in this situation, the iodine is actually going to be in the central atom. So it's going to be a hypervalent structure. So is there going to be resonance? Well, in this structure, we know that the halogens on the end, they're going to be participating in single bonds. So if there's only going to be single bonds, there's going to be no resonance structures. So no resonance. So let's draw the 2D Lewis dot structure for iodine, 3 minus. Okay, so let's check the structure to make sure everything is accounted for. So the iodines at the end, they have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7, right? So the formal charge of these iodines is 0. However, in the central atom, the iodine also needs to have 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8. So why does this structure have 8? Well, this 8 is to account for this extra, this minus that we have. So there's one more additional valence electron. So this actually has a formal charge of -1, right? Because iodine is supposed to have 7. 7 minus 8 equals -1. So that's why this structure has this negative associated with it. So I3 minus, the structure, the Lewis dot structure looks like this. So as we can see here, it's a hypervalent compound, right? It has more than an octet. So how many electron-rich regions are there? So let's count. 1, 2, 3, 4, 5. 5 electron-rich regions for the central atom. So what does this correspond to? What kind of electron geometry? Is what we call trigonal bipyramidal. Bipyramidal. Okay, so what kind of hybridization does the central atom have? So we know that it has 5 electron-rich regions. So we have sp3, so that's 1 plus 3, that gives us 4, so we need to have another one, d1. So sp3d, 1 plus 3 plus 1 gives us 5, right? That's the trick I taught you before in problems 1 and 2. So if it had, for example, 4 electron-rich regions, it'd be sp3, 1 plus 3, right? Okay, so for iodine 3 minus, we have sp3d. That's the hybridization. So what are the bond angles in this molecule? Well, for trigonal bipyramidal, you actually have 3 different kinds of bond angles, and I'll show you in a little bit when I draw the three-dimensional structure where all of these bond angles correspond to. Okay, so we have an 80, a 90, and a 120. So I'll show you when we draw this 3D structure where those bond angles are. So we have, let's look at the bonding pairs. So how many bonding pairs of electrons are there? So there's 1, 2, 2 bonding pairs. So how many unbonded pairs are there? 1, 2, 3 for the central atom. So let's draw what is the molecular geometry going to be. So the molecular geometry is going to be, in shorthand, it's going to be A, B, so for the bonded pairs we have 2, and the unbonded pairs we have 3. So AB2, U3. Now let's draw the 3D structure. Okay, so iodine 3 minus will look something like this. Again, I'm just drawing it as a triangle, not that there's bonds between the 3 electron pairs. It's that the 3 electron pairs are arranged to where it's going to be like a triangle. So the 120 degrees is between the electron pairs. So think of that there's a so if you think of the triangle, there's going to be 100 degrees between each adjacent electron pair, right? Between this bond, this and this, right? So that's 120 degrees. This and this, and then this and this is also going to be 120 degrees. Now 180 degrees corresponds to this iodine and this iodine. That's 180 degrees. And then the 90 degrees corresponds to this iodine, which is going to be perpendicular to the electron pairs, right? Because think of the iodines as going as straight up, and then think of the triangular arrangement of the electron pairs as flat. So see that it's perpendicular. So that corresponds to 90 degrees. So let's go to let's draw the dipoles. Well, there's actually going to be no dipoles for this molecule because the iodines, there's no electronegativity difference. So there's actually going to be no dipole, right? You only have dipoles if there's electronegativity differences, right? But because iodines, it's the same atoms, there's going to be no dipole. So how many sigma or pi bonds are there going to be? 2 sigma, right? 2 single bonds. And then lastly, is this molecule going to be polar? No, there's no dipole, so it's going to be nonpolar.